be the first tutorial for the Math 30 Applied course. I said I'd try and include one of these per unit. The topic of the tutorial, I said I'd try and keep the most difficult idea we cover in the unit. For this particular unit, there's nothing really, there's no big difficult idea that we cover. It's a lot of small ideas. And the real difficulty here is going to be after you've figured out, okay, I'm dealing with a probability question, asking yourself, all right, well, what strategy or what concept do I apply here to solve this? Well, there's going to be roughly one per topic in your book. Okay, so things, I'll start with the most blatant, that some of the time you'll have just a simple probability question where you're literally looking for the number of favorable outcomes over the total outcomes. So simple probability. You'll also have questions with the fundamental counting principle. If you remember, that was looking at your total number of choices. You'll have questions dealing with mutually exclusive events. Those are going to be questions where you see that word or are going to be the tip-off for those questions. Questions where you're going to use your equation for independent events. That's when you see that word and. And another type of question is going to be when you're going to see pathways. Those are going to be more obvious because you'll usually see a picture or diagram before you start the problem. So those are a little bit more obvious. So I'm going to show you 5 different problems. And each time before you see me go through the explanation, I want you to ask yourself, what principle or what formula am I going to apply to solve this question? Okay, in this problem, we have 2 cards being selected. It's with replacement, and the word and is used. So there should be 2 tip-offs here. If you ever see replacement with cards, you're not guaranteed to see card questions. You know it's going to either be a mutually exclusive question or independent question. That's a little bit more shaky as a reasoning. The thing that's more solid here is that word and. When you see the word and, it's asking for the probability of one thing and another. That's a real tip-off that it's independent, dependent events type question. Okay. Now, you should know what independent and dependent events are. Remember that if you have 2 events, if the first event affects the second, then it's dependent. If they don't affect each other, it's independent. So for notation, I'm going to write 5 of hearts and 2 of hearts. Okay, so this is the notation we were using. This just means probability of whatever's in the brackets. Remember that if I put a line over top of these, it means the probability of not getting it. It didn't ask me about that here. Okay, so this and word that was shown in the problem told me that it was an independent dependent type question. So the formula for that is going to be the probability of the first event times the probability of the second event. If you had 3 or 4 events, then it'd be the probability of the first times the probability of the second times the probability of the third, and so on. But we've only got 2 draws here. We've got 2 cards. So it's the chance of getting the 5 of hearts. And then we're going to multiply that by the chance of getting a 2 of hearts. Okay? So it's an independent dependent question. Once you've got past that step, it's actually pretty easy from there. That's the hardest part, is knowing what to use. Now we've said that for independent dependent, this is the formula on your formula sheet that you want to go to, and it says you want to take the probability of the first event and multiply it by the probability of the second event. Now where these things can get more difficult is ordering. Now the question says a 5 of hearts and a 2 of hearts, but it also gives you a hint. I'm just going to read here at the bottom. It does say at the bottom of the question, in either order. Now that's a tip-off that it's one of the more difficult types of question, and we looked at this in the notes. Because there is an order, it's actually a 5 of hearts and a 2 of hearts, or a 2 of hearts and a 5 of hearts. So when I write this out on the right-hand side here, I need to include this order and the reverse. So I basically have to do it twice. Okay, and I'll show you what I mean. So Now my probability, I'm just going to go 5H and 2H, is going to be what we had before, so probability of a 5 of hearts times the probability of a 2 of hearts. And I basically have to do the question all over for the other chance, so I'm just going to put in a plus sign for that. And then I'm going to do the probability of 2 of hearts and the probability of 5 of hearts. Okay, so now I've accounted for the fact that there could be a 5 of hearts first and a 2 of hearts second, or the other way around. I could get the 2 of hearts first and the 5 of hearts second. So from here I just got to plug in my probabilities. So what are the probability of getting a 5 of hearts? Well, that's one card of the deck, so it's 1 out of 52. What are the chances of getting a 2 of hearts? It's 1 out of 52. Okay. Then on the other side, again, the probability of getting a 2 of hearts is 1 out of 52. And the probability of getting a 5 of hearts is 1 out of 52. Your calculator is going to struggle to put this in fractions, so I'm going to try and do this avoiding the ugly decimals that it gives. Remembering back to your junior high days, if you multiply fractions, it's numerator, numerator, denominator, denominator. 52 times 52 is 2,704. Yes? And 1 times 1 is 1. So this section reduces to this. And then on our other side, 52 times 52 is 2,704, and 1 times 1 is 1. Okay. If you add fractions, you should remember that if they have a common denominator, it's as simple as adding the numerator. So this becomes 2 over 2,704. Okay? So this is our answer. We're told that the manager of a sports store wants these 5 tents to be positioned one over another, but there's some stipulations put on where they should be. If you read the information below, it says that the dome, rain, and spacious tents are blue. The scout tent is beige, the hiking tent is yellow. The blue tents can appear in any order, however, the manager does not want to have any one blue tent immediately after another blue tent. So it doesn't want the blue tents beside each other. This is the only restriction, and it's asking how many different positions are possible. Okay. Hopefully you would be able to figure out that this is a probability question, and then from there you need to know which probability principle to apply. So the main hint here is where it says positions. How many positions are possible? That's another way of saying how many combinations are possible. If you ever see combinations or something asking about how many elements are in the sample space, it's a fundamental counting principle problem. So that's where you need to start. You need to know that we're going to use the fundamental counting principle to solve this. It's similar to questions with how many phone numbers you can make, how many different license plate combinations you can make, things like that. Okay. Now, before I go into the specifics with some of those restrictions, I'm just going to draw a diagram. Anytime you can draw a diagram in math, do it. It's an extremely valuable thing to do. So I'm just going to make 3, 4, 5 dashes, and the dashes are going to represent the tents. You can do them across, it won't change the problem. And then what I'm going to do is I'm going to put in the number of possibilities at each point. Now, the fundamental counting principle basically will give you the total number of combinations you can get. And then all you need to do is at each point that you have a choice to make, you just write down the number of possibilities for that choice, and then we're going to multiply them all together. Okay, so for the first, third, and fifth, they need to be blue. So on your diagram, just to remind yourself, I would write in blue. First, third, and fifth. Again, if you're curious as to why I'm labeling these blue, it says in the problem that the the blue tents cannot be right beside each other, meaning there needs to be some sort of space between any of the blue tents. That's why I'm making them 1, 3, and 5. And after that, we have yellows that go in here or here, okay? So I'm going to start at the top. Now, in my first option here, how many choices do I have? Well, there's 3 blue tents. I can put any one of the blue tents in this spot. So I have 3 choices here. I'm going to skip this one. I'm going to go to here. If I had 3 blue tents total, if I put one of them here, I've only got 2 left to choose from. Those 2 can go in either spot. So of the remaining 2 blue tents, either one can go here. So I'm going to put in at 2. So we've used one here. We've used another tent here. So that leaves us with only 1 tent left. So there's actually only one possibility for the last tent, okay? With that in place, that's the hardest part. Now with the yellow tents, I can put either one of the yellow tents here. So I have 2 choices for this spot. But if I do pick one of the yellow tents to go there, there's only one possibility left over here. The other yellow tent has to go here, okay? As I said, with the fundamental counting principle, you're gonna multiply all your, every time you have a choice, you're gonna multiply. You're used to seeing it like this. This one happens to be vertically, so you're just going to multiply all these together to get your total possibilities. If you multiply all those numbers together, 3 times 2 is 6, 12 stays at 12. So we're left with 12 total possibilities for how these tents can be positioned. Okay, so the next problem we're looking at is a theory problem. You're going to see a good number of these as well, and you need to know the key differences between mutually exclusive and independent events. That's actually one of the trickier parts of this unit. Okay. Now, if you read through the problem, it says that there's a roulette wheel. There's 18 red numbers, 18 black numbers, and 1 green number. And it tells us that a spin has the ball land on a red or a black. Now, the lower level of understanding would give the problem away as is. It's not as solid, but if you remember, we used the OR formula, A or B for mutually exclusive events, and we used the AND formula for independent events, A and B. So with that alone, you would immediately guess that it would be C, mutually exclusive events, because you see the word OR in the problem. That's not really a great way to justify it, but it would get you the right answer in this case. It is C. A better way to look at it would be asking yourself, does one event affect the other first for independent events? Well, one event affecting the other would mean 2 events. If there's a single event, the idea of independent-dependent isn't there, because we can't have one thing affecting the other because there's only one thing. The only question here is, of that one thing, that one event, can that one event actually fit both categories, black or red? And the question there would be, is this mutually exclusive or not mutually exclusive? Okay, now non-mutually exclusive isn't actually one of our options there, so it's not even a question here. But if you're wondering, a red number and a black number, there's no overlap there, they're separate, so they're mutually exclusive. Complementary events, remember the complement is just the chance of not getting something. They don't ask about that. A sample space is just your list of possibilities. That's not mentioned either. So again, either through knowing that you see the word OR there, or realizing that there's only a single event, you should be able to come to the answer that C is your only option for this one.